Hey there, and welcome to This Explainer. Today, we are taking a fascinating journey straight into the microscopic world of the invisible brains that power, well, our entire modern existence. If you're watching this right now, chances are you are using the exact technology we're about to decode. We're going to completely break down the anatomy of a microchip, and we're specifically zeroing in on the incredibly influential ARM architecture. It is an absolute marvel of engineering, and I promise you, by the end of this, you're going to see your everyday gadgets in a completely different light.
So, you might be wondering, why ARM? Well, consider this staggering figure, 90%. A massive 90% of the mobile market is ruled by ARM architecture technology. That is just wild. It doesn't just happen to be a popular choice, it is literally the fundamental bedrock of mobile computing. When we talk about ARM, we aren't just talking about one specific piece of hardware. We're talking about the dominant standard that basically shapes how information is processed all around the globe.
And you know, we're not just talking about the smartphone in your pocket. Let's ground this in reality for a second. Think about the vast, everyday array of devices this architecture enables. We are talking about everything from the smart chips in your credit cards and the digital TVs sitting in your living room, to legacy PDAs, high-speed gaming consoles, and even the complex digital dashboard controls in modern cars. ARM is essentially the beating heart of all these embedded solutions, enterprise systems, and home electronics.
To keep things from getting overwhelming, let's set a clear roadmap for our technical anatomy lesson today. First up, we'll cover the ARM dominance. Then, architecture and pipelining. Third, we'll navigate memory interfaces. Fourth, we'll look at debugging the system. And finally, we'll bring it all together with the LPC2148 microcontroller. All right, let's jump right into Section 1, the ARM dominance and why it really is the heart of the machine. Think of the ARM processor as the high-performance core. It's the absolute center of the system. Just like every organism needs a heart to pump life through its veins, in our technological organism, that heart is a highly specialized, optimized processor. Specifically, we're looking at the ARM7 TDMI. Now, this is a member of the advanced RISC machines family, and RISC just stands for Reduced Instruction Set Computer. But why is this specific 32-bit microprocessor the heart of our tech titan? Well, because it achieves the absolute holy grail of hardware engineering. It delivers exceptional high performance while demanding very low power, all at a really low price point. In the embedded systems world, balancing power and performance is everything. It's make or break. And the ARM7 TDMI, it masters that balance beautifully.
Moving right along to Section 2, architecture and pipelining, or as I like to call it, the brains factory.
So if the processor's the heart, the architecture is the blueprint of the factory. It dictates exactly how the chip fetches and processes instructions to actually, get work done. At the very foundation of this factory, we have two primary architectural models. First is the von Neumann machine. Here, data and program memory share the exact same space and bus. Think of it like a single-lane highway. Cars heading to the data center and cars heading to the program center have to share the exact same road. It can get backed up. Then you have the Harvard machine. This model separates the data memory from the program memory. That's your dual-lane highway, allowing traffic to move simultaneously without bottlenecking. Now, while the core ARM7 architecture uses a von Neumann-style structure, later iterations, like the ARM9, actually adopted the Harvard architecture for even greater speed.
And this brilliantly illustrates that highway analogy. When you map out the von Neumann machine, it routes both data and address lines right through one central CPU bottleneck to a combined memory block. But the Harvard machine elegantly splits that flow. Program memory gets its own instruction address pathway, and data memory gets its own totally separate variable address pathway. By separating these pathways, you can theoretically double your memory access throughput. It's a real game changer. Okay, so once the data gets into the CPU, how does it actually process it? This is where pipelining comes in. The ARM7 uses a snappy three-stage pipeline: fetch, decode, and execute. Think of pipelining as a highly efficient factory assembly line. Without a pipeline, a processor has to finish one entire instruction before it even thinks about fetching the next one. But with pipelining, the processor is fetching the next instruction while the current one is being decoded, and while the previous one is being executed. By utilizing this instruction-level parallelism, the CPU drastically increases its throughput and overall speed. It's multitasking at its finest.
But here's a really interesting problem. 32-bit instructions take up a lot of memory space. So what if you need to squeeze more code into a tiny little embedded chip without losing the processing power of a 32-bit register? Enter the thumb instruction set. The big idea here is a super reduced instruction set that is only 16 bits long. It's a brilliant solution. It allows developers to get basically twice the code density of standard ARM code while still running on the exact same powerful 32-bit internal register set. It is literally like zip compressing your factory's blueprints so they take up half the filing space, but you can still use them to build the exact same massive machines.
Okay, let's dive into this next part. Section 3, Navigating Memory Interfaces, the nervous system.
We've explored the heart, we've looked at the factory, now we need to understand the nervous system. This is the complex, intricate web of memory bus cycles that dictate how data travels across the entire architecture. The ARM processor accesses memory using 4 different transfer cycles, and it's all dictated by 2 critical signals, NMRQ and SEQ. By combining the states of these 2 signals, the chip figures out how to route the data. For instance, 2 zeros trigger an N cycle or non-sequential cycle. That's where memory access is completely unrelated to the previous transfer. A 0 and a 1, that triggers an S cycle or sequential cycle, which is heavily used for rapid burst data transfers where the location is right next to the previous one. A 1 and a 0 is an internal cycle, meaning no actual memory access is performed, it's just doing internal execution. And finally, 2 1s trigger a coprocessor cycle. This logic matrix is essentially the routing brain for all the system's data.
Now, what's really interesting about this is how it maps those theoretical memory cycles onto a concrete hardware clock timer. When you visualize the master clock ticking away, you can see how an N cycle initiates the very first memory access at a specific address, but then look at how the processor seamlessly shifts into S cycles for the subsequent addresses right after it. This timing beautifully proves how sequential cycles allow for super rapid burst data transfers on the bus without having to renegotiate completely new, unrelated memory addresses for every single tick of the clock. It's incredibly efficient.
Which brings us to Section 4, Debugging the System, or to keep our biology theme going, the immune system.
If we treat this microchip as a biological entity, debugging is absolutely its immune system. It's the system's built-in ability to be probed, diagnosed, and ultimately healed when the software or the hardware just isn't acting right. The ARM7 TDMI contains specific, dedicated hardware extensions purely for this kind of advanced debugging. The standard interface for this is based on the IEEE JTAG standard, that's short for Joint Test Action Group, and working right alongside JTAG is the embedded IC macro cell. This is an incredibly clever unit powered by breakpoint and watchpoint registers. When a specific condition is met, these registers work together to physically halt the ARM core. This allows a human developer to freeze time, read the status, and do active, real-time debugging without destroying the system's current state.
To put that into perspective, in the real world, this involves a human operator using a debug host, basically a regular PC running software like the ARM debugger for Windows. This host issues high-level, human-readable commands which pass through a protocol converter. That converter translates those commands into the low-level electrical JTAG signals that the debug target, the actual ARM processor, can understand. It's a literal translation bridge connecting our macro world to the micro world of the chip.
Finally, let's bring it all together in Section 5, the LPC2148 microcontroller, the complete organism.
Up until now, we've been zooming in on the microscopic details, the core, the pipeline, the memory buses. Now we are zooming all the way out to look at a fully integrated, commercially available chip. I know, looking at the full schematic, it looks like a giant, overwhelming puzzle. It's incredibly complex, but don't let it intimidate you. Actually, if you look closely, this diagram is simply all the concepts we just talked about combined into one single physical package. Right there in the center, you have the ARM7 TDMI as processor core, and attached to it are all the memory controllers, the debugging interfaces, timers, and input/output pins that make this not just a processor, but a truly complete, standalone computer on a single chip.
So what you really need to take away from this is the greatest hits of that massive diagram. The LPC2148 brings together that highly efficient 32-bit ARM7 CPU we discussed, and it pairs it with a healthy 512 kilobytes of on-chip flash memory. Furthermore, it integrates incredibly useful peripherals directly onto the silicon itself, things like a USB 2.0 device controller for high-speed data transfer and sophisticated clocking mechanisms known as dual-phase locked loops.
Speaking of those phase-locked loops, or PLLs, they are absolutely crucial. They act as the precise pacemakers keeping this entire organism running in perfect synchronization. The chip takes in a basic, relatively slow crystal oscillator input, usually between 10 and 25 MHz. But the internal PLLs act as multipliers. PLL0 takes that base frequency and multiplies it up to a zippy 12 to 60 MHz for the main system clock. Meanwhile,
PLL1 provides a very specific, perfectly steady 48 MHz clock that is required strictly for the USB interface. It's a literal masterclass in localized, highly controlled power management.
And that brings us to the ultimate question. We've decoded the incredible anatomy of the ARM architecture, from its microscopic assembly line pipelines to fully integrated standalone microcontrollers like the LPC2148. But as these chips grow ever smaller, ever more power efficient, and vastly more capable, what exactly is the evolutionary path for the traditional embedded business? I mean, what impossible future technologies will this invisible foundation unlock next? Keep that question in mind the very next time you tap your smartphone or start your car. Thanks so much for watching, and keep learning.